Welcome back to the Deep Dive, everyone. Great to have you with us, especially our Before AGI podcast community members. You're here because you get it. When you're training these huge AI models, picking your optimizer, that's not just some minor setting. It's probably the core strategic choice you make. We know you're ready to go beyond just hitting Adam and hoping for the best. We're here to really understand that lost landscape.
Right. Training AI is, at its heart, an optimization puzzle. And that classic analogy, it still works wonders. Imagine you're blindfolded, on a mountain, thick fog all around. Your mission, find the absolute lowest point, the valley floor. That's minimizing error for our model.
Exactly. And basic gradient descent, it just points downhill, tells you the steepest direction. But the step size, if it's fixed, well, that hiker's in trouble. Too slow on gentle slopes, or maybe takes a massive leap right off a cliff in a steep bit.
Totally suboptimal, especially when that mountain, the lost landscape is, incredibly complex. Millions, maybe billions of dimensions with canyons, plateaus, sharp drops. It's wild terrain. So our job today, give that hiker the best gear. We're diving into these advanced adaptive optimizers. We'll hit Adagrad, then RMSprop, and wrap up with this really interesting meta strategy called Lookahead. The goal isn't just formulas, it's the intuition, why they work, and crucially, when you should actually use them.
Okay, let's start at the beginning then. Adagrad adaptive gradient algorithm. Huge deal when it came out. It was the first big step away from that single fixed learning rate. It gave each parameter its own rate. So how does it do that? How does it know the terrain for each weight?
Well, think of it like giving our hiker a perfect lifelong map of every single step they've ever taken. Adagrad keeps track. Specifically, it accumulates the square of every gradient it sees for every single weight individually.
It accumulates the squares, so what does that do?
It acts like a memory or maybe a penalty system. If a particular weight, say, one connection has seen a lot of action, lots of large gradients in the past, its accumulated sum of squares gets really big. Then, when it's time to update that weight again, Adagrad uses that big sum in the denominator. It divides the step size by essentially the square root of this historical sum. So big history means tiny step. Small history, bigger step.
Ah, okay. So it forces caution on paths that have been historically steeped or busy.
Yeah.
And then immediately tells you where it shines, right? Sparse data, things with sparse features.
Exactly. Think about natural language processing, NLP. You've got tons of common words, the, is, and. They pop up all the time.
Generating gradients constantly.
Precisely. Adagrad sees that flood of gradients, their squared history balloons, and boom, their learning rate gets slashed way down. But then you have these rare words, maybe specific technical terms or names or unique IDs. They appear maybe once in thousands of examples.
Sparse, but potentially really important for the meaning.
Critically important. Because they generate gradients so rarely, their squared gradient sum stays tiny. Adagrad doesn't penalize them much. It lets them keep a larger step size, effectively amplifying their signal. That per-parameter adaptation was key for early large-scale stuff. Like, remember Google's early deep learning work? That famous cat detector finding cats in YouTube videos? That was trained on super uneven, sparse data, and Adagrad was crucial.
But there's always a but, isn't there? What's the catch?
The catch is baked right into that core mechanic. That accumulated sum of squared gradients, it only goes up, it never decreases, it's monotonically increasing, which means the effective learning rate for every single parameter is constantly relentlessly shrinking towards zero.
So the hiker just gets slower and slower
Yeah.
and slower forever.
That's exactly it. Even if a parameter moves into a completely flat, easy region later in training, it's still haunted by the steep hills it climbed way back at the beginning. That's the famous vanishing learning rate problem. Learning just grinds to a halt. For the really deep networks and long training runs we need today, Adagrad often it stalls out way too early. The hiker gets stuck taking these microscopic steps, never quite reaching the bottom of the valley.
Okay, clear problem identified. Infinite memory is actually a curse here. We need something that remembers recent dangers but forgets the ancient history. Which brings us neatly to RMSprop, root mean square propagation. How did it fix Adagrad's stalling problem? How did it learn to forget?
Right. It basically swapped Adagrad's perfect lifetime record for something more like short-term memory. Instead of just summing up all past squared gradients forever, RMSprop uses an exponentially decaying moving average.
Exponentially decaying. Okay, unpack that a bit.
It means recent gradients count much more heavily than gradients from long ago. There's a new hyperparameter, usually called beta, often set around 0.9. This beta controls the forgetting rate. A beta of 0.9 means the current squared gradient gets, say, 10% of the weight, and the old moving average keeps 90%. Over time, the influence of very old gradients fades away exponentially. This stops that denominator, the historical penalty term, from just growing infinitely large.
Got it. So if the hiker was in a really rough patch thousands of steps ago, Adagrad holds onto that grudge forever. But RMSprop says, that was a while back. Things look smoother now, let's adjust.
That's the core idea. It lets the learning rate adapt to the local shape, the recent curvature of the loss landscape. You keep the pro-parameter adaptation, which is great, but you ditch the self-sabotage of the learning rate vanishing completely. It allows for much longer, more stable training.
Stability sounds like the key word there. Where does RMSprop really make a difference?
Well, it tends to work really well in what we call non-stationary environment situations where the optimal direction might change over time. Jeff Hinton, who first proposed it, specifically mentioned its strength for training recurrent neural networks, RNNs, and LSTMs. With sequential data, the optimization landscape can shift as you process the sequence. RMSprop's shorter memory, its focus on the recent past, makes it much more robust there than Adagrad. It's become a really solid, reliable default or baseline for many deep learning tasks.
Okay, fix the vanishing rate. But like we said, optimizing often just shifts the challenge. What's the trade-off with RMSprop? Where's the new tuning headache?
The trade-off is definitely hyperparameter sensitivity. We fixed Adagrad's built-in decay flaw, sure, but now we have two really important dials to tune. That main learning rate, eta, which still sets the overall scale, and that decay factor, beta. Getting beta wrong or eta wrong can really impact performance. RMSprop can still oscillate or converge poorly if you don't tune those carefully. It demands a bit more attention from the practitioner.
Right. So we've seen adapting step size based on history, whether long-term or short-term. Now let's shift gears completely. We're moving from tweaking the step itself to optimizing the whole process of optimization. Let's talk Lookahead. You called it a meta-optimizer. It's not changing the step directly, it's changing the strategy. The fast scout steady army analogy really clicks for me here.
Yeah, Lookahead is conceptually different. Its main goal isn't just speed, it's about slashing the variance of the updates, making the whole journey smoother, more reliable. And it does this with this cool dual weight system.
Dual weights, okay.
So you have an inner loop. Think of this as the fast scout. You take a standard optimizer, maybe Atom, maybe RMSprop, something solid, and let it run ahead for, say, pay steps. The scout explores quickly, maybe zigzags a bit, reacts fast to the immediate terrain. It's potentially noisy.
And the actual model weights, the ones we care about, or the steady army.
Exactly. That's the outer loop. The main model weights the army. Don't just blindly follow the scout's erratic path. Instead, the army waits until the scout finishes its kill of steps. It sees where the scout ended up. Then the army updates its position, but it only moves part of the way towards the scout's final position, usually controlled by another hyperparameter, alpha, maybe 0.5. So it interpolates.
So it's like averaging out the scout's potentially jumpy exploration. It takes a smoother, more considered step based on where the exploration ended up.
Precisely. That interpolation, that averaging, has this powerful smoothing effect. The scout might bounce around due to noise in the gradients or tricky local minima, but the army follows a much more stable, direct path towards the overall goal. That directly translates into better stability during training.
And stability is gold, especially with some of the trickier models out there now.
Absolutely. Lookahead isn't just a theoretical nicety. It's become a really important component in state-of-the-art setups. You often see it wrapped around other optimizers, like in the Ranger optimizer you mentioned. It helps achieve top results, especially when training things that are notoriously unstable. Think generative adversarial networks, GANs, or these newer diffusion models, preventing mode collapse, managing wild gradients. Lookahead really helps tame those beasts.
Sounds incredibly useful, almost like a cheat code for stability. But it's a wrapper, so there must be some practical considerations or downsides.
Yeah, there are a few, though usually minor compared to the benefits. First, Lookahead doesn't magically fix a bad underlying optimizer. You still need to choose and tune that base optimizer, the scout, reasonably well. Second, it introduces two new hyperparameters: Grawlers, the number of scout steps, and alpha setter, that interpolation factor.
More knobs to turn.
More knobs, yes, but the good news is that the defaults like pay5i and alpha, $5.55 often work surprisingly well out of the box, so it's not usually a huge tuning burden. The main practical thing is a slight increase in computation. You're running those staller inner steps before each main update, so there's a bit more work, but usually the faster conversions and improved stability more than pay for that overhead.
Okay, this gives us a great toolkit. Adagrad, RMSprop, Lookahead. Three very different approaches. Making the right choice here seems critical for performance, efficiency, saving compute time, everything. Let's try to synthesize this into a practical guide for listeners. When do you reach for which tool?
Okay, let's pull it together. We've journeyed from Adagrad's perfect but flawed memory to RMSprop's adaptive short-term view to Lookahead's strategic stabilization. So, Adagrad, it's your specialist tool. If your problem is defined by extremely sparse features, think massive embedding layers in NLP or certain recommendation systems where rare items are vital, Adagrad's ability to boost those rare signals is unique. Start there, but keep a close eye on that learning rate. If you need a really long training run, be prepared for it to potentially stall out.
And when it does stall, or if sparsity isn't the main issue and you just need a solid workhorse?
That's when you bring in RMSprop. Think of it as the robust general-purpose choice. It's particularly good if Adagrad is stalling, or for those non-stationary tasks like RNNs and LSTMs where the landscape changes. It provides stability and keeps learning going.
Okay. And then let's say you've got RMSprop or Atom tuned pretty well, but training's still a bit shaky, maybe oscillating, or you're working with something inherently unstable like a Jan.
That's prime time for Lookahead. Use it as a wrapper. It's relatively low risk, high reward. Layer it on top of your already tuned base optimizer. Its specific job is to smooth things out, reduce that update variance, and guide the training more reliably towards a good minimum, especially in tricky situations.
Fantastic. So we started with this image of a blindfolded hiker stumbling around. Now we've given them Adagrad's map of past terrain, RMSprop's awareness of the immediate surroundings, and Lookahead's strategy of sending out a scout before the main army moves. We've turned that blind stumble into a much more sophisticated, well-equipped expedition.
Definitely. And the field doesn't stop there, of course. What's really exciting now is seeing how these ideas get combined. People aren't just picking one, they're building hybrids. You mentioned Ranger that combines RADOM, a variant of Atom, with Lookahead. There are things like NRMSprop adding Nesterov momentum. We're constantly blending adaptive rates, momentum, variance reduction, trying to find the ultimate combination.
So the final provocative thought for you, the listener, to chew on. As models get even bigger, even more complex, what new hybrid optimization strategies combining these principles in novel ways will be needed to unlock that next level of training efficiency and find even deeper valleys in that lost landscape?
Something to think about. Happy training out there.
We really hope this deep dive helps you navigate the optimizer choices more confidently and move beyond just the standard defaults. It can make a huge difference. If you want more AI concepts broken down like this, please make sure you subscribe to the Before AGI podcast. Join the community, share your thoughts. And if you're looking to actually implement some of this, see coding examples, get hands-on tutorials, and more deep learning insights, definitely check out the affiliated YouTube channel, Ian Ochieng AI. That's O-C-H-I-E-N-G. We've got lots more content there to help you on your journey. Until next time, may your loss curves always be smooth, or at least trending downwards.